So, welcome to the 13th session on the course on signals and systems. Let us take a quick moment to recapitulate the important result that we saw in the previous session. It was obtained by a small rearrangement of the shifting property. So, let us recapitulate that idea. We had said that an integral from minus infinity to plus infinity xt delta t minus t0 gave us x at t0, and we noted that we could choose delta t symmetric about 0. So, we could choose delta t like this. I am showing delta as a function of another variable which we call lambda, and here of course I must clearly make it a delta, capital delta, to emphasize the point that it is spread over an interval of delta. So, delta lambda is equal to delta capital delta of minus lambda. So, it is an even function of lambda, and therefore, we said that delta t minus t0 is equal to delta t0 minus t, and therefore, we came to the important conclusion that the integral from minus to plus infinity xt delta t0 minus t, of course here the integral was with respect to t, and here that is also with respect to t, is equal to x at t0. So, here this integral should have been with respect to t, that is all right, that is understood. But now you see there is something important that we should note here. You see, the meaning of this equation here, this equation and this equation here have a totally different meaning. The first equation says that when I multiply xt with delta t minus t, so when I multiply a continuous function with a narrow pulse and integrate it, keeping that pulse of unit area, I get essentially pick up or shift the value of the input or the function xt at the point at which the pulse is located. Look at the second equation. The second equation says something totally different. It says if you take t0 now to be the variable, so we will now think of t0 as the basic variable by which the function is indexed, and this is the variable of integration t here. This is the variable of integration. So, what we are saying is, now take any particular point t. T0 is the index variable on the input. So, what we are saying is, if you take the value of the function x at a particular point t, which is x at t, and multiply it by a narrow pulse which is essentially centered around any point t0, and take a sum over all such t, and that sum becomes an integral in the limit. A totally different interpretation. Listen carefully. I am repeating it. Let us look at the equation again. Any particular point t, the value of the input at that point t, an impulse or a pulse for the moment, not an impulse, a pulse placed at the point t with the indexing variable t0. What I mean by the indexing variable is the variable with respect to which you describe the function x, integrated over all t. Now, the integral here should be interpreted as a limit of a sum. So, integral is essentially a limit of a sum. So, you could think of it like this. You could think of it as x at some t1 delta t0 minus t1 plus x at some t2 delta delta T0 minus T2 plus and so on. Take these T1, T2, T3 and so on as close as you can make them. And in fact, what we are saying is, let me show it graphically now. You must understand the same thing in many different ways. So let's show it graphically. What we are saying is, pick a T1 here, pick a T2 there, pick a T3 there, and this variable is T0. That's what I mean by the index variable. Put a pulse here, put a pulse there, put a pulse there. Put a pulse here. And this width, as you know, is delta. That's why we are calling it delta, capital delta. This height would now be 1 by delta multiplied by x at T1. Now do the same thing at T2. Let's use a different color there. So again you have a width of delta here and a height of 1 by delta times x at T2 here. And once again put another pulse here, width delta, height 1 by delta times x at T and so on. Now visualize putting pulses at every T0. So here you have x at T1, you have x at T2 and so on, and maybe you have a function that goes, let me show that function in some, let's say the red color again. You have some continuous function here which goes like this perhaps. This is actually, graphically we are trying to show 1 by delta times x of T0 here. Visualize putting pulses at every T0. And now, because you have a continuum of pulses, you see there are not discrete points, but there is a continuum of pulses. At every point there is a pulse, so to speak, and all these pulses need to be combined, and their combination leads you into the function x at T0 under the integral sign. So you see the integration is required because you have unit area contained in each pulse. So go back to the diagram. So you visualize putting pulses at every T0, and now one more thing you need to do is to visualize delta going towards 0. I know this requires a little bit of work, you do need to visualize first an infinity, a continuum of pulses, and then you need to visualize each of those pulses becoming smaller and smaller in width and all coming together under an integration. And then what we are saying in this equation, let us write that equation again. What we are saying in this equation, namely x at T0 is equal to, now here I intentionally show it in a different color, x, we will show the variable of integration in a different color. So x of t and then delta delta. So here T0 I will keep as it is, and then minus we have the variable of integration again. So here this makes a totally different statement. This says that every function is a combination of an infinite number of such pulses, such very narrow pulses. This is a very important idea. Now these very narrow pulses that we are talking about here, so these very narrow pulses with a height of 1 by delta and a width of delta, which means they enclose an area of 1. The area enclosed is delta into 1 by delta, which is 1. The area remains intact even as the pulse becomes narrower, that is delta tends to 0. This ever narrowing pulse is a new idea to us, and we shall talk about it more in the session to come.